Good afternoon, everyone. So let us start. So first thing is that unfortunately, due to the technical issues, the lecture video for the last lecture was missed. So I don't know. Maybe the SD card memory was inappropriately cleared by someone else. So anyway, it's missed. But from today, the lecture video should be streamed directly to the YouTube UFU data channel. So I have made an announcement in the Canvas, and you will know how to access the UFU data channel. And also, whenever our lecture are finished, I will try to paste the link to the course webpage so that you can access them directly. But just be aware, because of technical issues that often happens, the video might not be up to date, or sometimes it could be missing. So please bear with that. And also, I highly encourage you to come to the lecture. That's the most effective way of learning, because you just follow with me and read the lectures and discuss. I think nothing more effective than this way of learning. Otherwise, you spend like hours and hours watching the videos, tedious, right? So, yeah. Okay, so let us continue the decision tree. So we have introduced the concept decision tree. Right? Decision tree is a hierarchical representation of the data set, and then we learned the classical decision tree learning algorithm, namely how to construct a decision tree from a set of training data. This algorithm is ID3. Essentially, is a greedy heuristic algorithm. We want to create a tree to be as small as possible to make our prediction to be more reliable. This is under the guidance of the so-called Occam's razor's principle, right? And then today we're gonna talk about extensions based on ID3 algorithm, and also some common issues when you use decision trees in practice and how can we solve them. So after today's lecture, you should be able to implement your own decision tree, which is robust and perform quite well in practice. After you can solve at least 80% of your practical machine learning jobs. So here are the outline. So first, we'll introduce several variants of decision tree. So all those variants are based on the same ID3 framework. You can just use the same recursive algorithm framework by replacing the information gain with other types of gain. You end up with different variants. And as to which measurement is better than the others, honestly, there is no guarantee. It only depends on your specific applications. But I just introduced other commonly used metrics. And then we'll talk about tricks to handle examples with missing feature values. That's pretty common in practice. And how can we predict the example when some feature value is unknown? Or how can we train a set of how can we train our decision tree from the training set with examples missing several feature values? How to deal with non-Boolean features? Right? If the category feature contains too many values, like 1,000 values, 10,000 values, you have to create like 1,000 branches or 10,000 branches. That's too large. Break our principle to make the tree to be as small as possible, right? And how can we deal with that? And finally, a very important concept, overfitting. We'll introduce what is overfitting and what is the harm of overfitting. How can we avoid? And you will say, actually, the classical ID3 algorithm tend to overfit the training data. That's not a good thing. We need to avoid that. And what kind of strategies can we adopt to avoid our decision tree overfit data? Okay, so before we introduce some variants of decision trees, Let us just briefly review the algorithmic steps of classical ID3. Right? So basically ID3 is a recursive algorithm, meaning that it will repeatedly call itself to create new tree nodes and branches, right? And until the current node has all the examples being labeled uniquely, right? Purely labeled, then we stop. Although, of course, we have other corner case like if the attribute set is empty, we have to stop because we don't have any attribute to split for the split data. Right? So to emphasize, the input parameters of decision tree are S, the current set of training examples, labels, the labels for all the examples in S, and candidate attribute set. We'll choose one attribute from this attribute set to split the current data. And then we'll run ID3, we'll call ID3 algorithm. We'll first check whether we have met the stopping condition. Right? So the stopping condition would be if all the examples have the same label, or if the attribute candidate set is empty. Right? Otherwise, we can perform split. Right? How can we perform split and create new tree nodes? We first create a root node for the current subtree. And this root node actually represents the current subset of examples S. And then, from the set of attributes, we select one which best splits the current example set S. And later we'll discuss how we choose the best attribute, right? And then suppose we have identified such a best attribute, then we'll just enumerate all possible values V that this attribute A can take. And for each specific feature value V, we create a new tree branch that corresponds to A, B, and V. And then we denote, we collect the subset of examples in S, where each example has feature A taking the value V. This is called SV. It's denoted by SV. So now we need to deal with two cases. First, if SV is empty, what should we do? What should we do? What if there is no examples in S has feature A in B? What should we do?
Most common label.
Yeah, most common label. So remember, this is a corner case. It's a very important corner case. Without this case, you might have some test example infeasible to be predicted with your decision tree. You're stuck at the internal node because you do not have any branch like going through V, right? A, B, and V. So when SV is empty, we need to create a leaf node. But the label for the leaf node is just taken the most common value of the labels in S. Otherwise, if SV is not empty, we are good, and we'll go ahead to call ID3 algorithm again. Right? So we are aware the calling of ID3, the recursive calling of ID3 here. So now the data subset becomes SV. Right? All the examples are in S whose feature value of A being V. And then for the candidate attributes, we need to remove A because we have used A to split the data set. So in the following splits, in subsequent splits, we won't use A anymore. So we need to remove A from the attribute set.
This is silly, but could you tell me what V is again?
V?
V. Yeah.
V is some specific value of feature A can take, or attribute A can take. So suppose, like for one particular feature or attribute is overlook, right? And then could be sunny, could be rain, could be overcast, right? So that it can take 3 possible values. So V is one specific value that feature A can take. And here, recursive calling label corresponds to the labels in every example of SV. Everyone is comfortable with this algorithm, right? Okay, great. So this is the whole framework of like ID3. So it is essentially a greedy heuristics. Why it is greedy heuristics? Because according to Occam's razor's principle, we want to find out a decision tree to be as small as possible. But enumerating all possible decision trees and find the smallest is a combinatorial search. It is not practical at all. So that's why we use this heuristic search. Every time we just choose one attribute that can increase the purity of the splitted data set. So because every time you perform split, you increase the purity, you can expect that by using this heuristic, you can arrive at the leaf node to be as early as possible. That's the key idea of this greedy heuristic algorithm. Then the question would be, how can we select one attribute that best splits the data set S? In other words, how can we select an attribute that can lead to the largest improvement of the purity? Yeah, exactly, right? That's what we discussed in the last lecture, right? We first, to measure the purity, we introduced the concept called entropy, right? So entropy indicates the uncertainty of the labels in data. So obviously, if you have no uncertainty, meaning that your data are uniquely labeled, otherwise you must have some uncertainty. So uncertainty indicates purity, and the larger the uncertainty, the less the purity, the worse the purity. Imagine if you have half labels to be positive and half examples to be negative, then you reach the maximum uncertainty, right? Positive example, negative example both have a 1/2 chance. Do you have any questions? At that time, we know that half positive examples, half negative examples, your purity is worst. On the other hand, if there's no positive examples, there are only negative examples, you reach the maximum purity. At the same time, you have at least uncertainty because all the examples are negative. You are sure about every example is labeled. So entropy is a typical indicator for purity, and the larger the entropy, the worse or the smaller the purity. That means the reduction of entropy indicates increase or improvement of purity, right? That's how we define information gain here. So we define the information gain for an attribute A as subtracting the entropy of the entire set S by the weighted summation of the entropy for each splitted data set. So here we need to be aware of the weighted summation here because we need to account for the size of each splitted data subset. Obviously, the larger the subset, the more influence it will have for the algorithm. So we do the weighted summation. So this is the size of each data subset SK. And this is the definition of the entropy. And we have mentioned that in detail in the last lecture. So now, in our ID3 algorithm, every time when we select attribute, we just evaluate the information gain of each attribute. Then select the largest, select the attribute which has the largest information gain. That means which has the largest reduction of uncertainty, equivalently, which has the largest improvement of the purity after splitting the data set, right? Everyone is good at this point, right? Okay, so any questions? Okay. So the problem is that, is this the only way to define the purity, only way to define the gain, to select the best features? Anyone give me some hint or intuition? Just tell me yes or no.
It's probably not the only way to do it.
Yes, of course, right? The purity, what is purity? Uncertainty. Purity can be expressed as uncertainty, right? But it can also be measured by other measures, right? So here I give you two examples, two other commonly used alternatives to entropy. So the first example is called majority error. So majority error is defined as follows. Suppose the tree was not growing below some node, and the majority label in the current data set were chosen to predict every example. Then what would be the error? So let us look at a concrete example. Right? Say, suppose at some node we have 20 examples in total, and 15 are positive and 5 are negative. Then what is the majority error? What is the majority error? So first, what is the majority label? Positive, right? So majority error requires us to use majority label to predict every example. So how many mistakes will we make? 5, because there are 5 negative examples. Well, all the other 15 examples, because they are positive as well, so our prediction is correct. So only make 5 mistakes, then the majority error is 5 over 20, right? It's 1 over 4. So now let us think. Does majority error reflect purity as well? To see this, we can consider like two extreme cases, right? So first, suppose the 20 examples are all positive. What is the majority error? 0, right? Or the 20 examples are all negative. What is the majority error? 0, right? Majority error is always non-negative. That's for sure, right? And 0 means it reaches the minimum. So when all the examples are positive or all the examples are negative, it indicates that we reach the maximum purity, right? On the other hand, if there are 10 positive examples, 10 negative examples, what is the majority error? I mean, half examples are positive and the other half is negative. What is the majority error? Half, right? So you can easily prove that majority error is at most half. Very easy to prove. But when the data set is split into half positive, half negative, what does it mean in terms of purity? Worse purity, right? Half of them are positive, half of them are negative. So now we can say the correspondence between majority error and purity, right? Then purity reaches the maximum. Majority error goes down to 0, right? Then purity becomes worse. The becomes least or worst. Then the majority error becomes largest. So similar to the entropy, right? The larger the majority error, the smaller the purity, right? In other words, the smaller the majority error, the larger the purity. So now, how can we define a new gain based on majority error? An idea? Yeah, exactly, right? You just replace entropy by majority error here. The other things are exactly the same. So the larger the majority error, the worse the purity, right? The larger the entropy, the worse the purity. The same thing, right? So that means the reduction of the majority error indicates the improvement of purity as well. So we can definitely define the majority error here. By the majority error over the entire data set, subtracted by the weighted summation of the majority error over each split data subset. So now you can simply use this majority error gain in your ID3 algorithm to select the attribute that best splits the data. That's the first variant of our ID3 algorithm. Does it make sense?
Does this only work with binary data, or is there an option for like entropy add?
It is you can imagine this can work for multi-class data as well, right? Because majority error, it can.
Could you get more than 50% majority error if you had if it was not if it was more binary?
I wouldn't think it's feasible. You can prove that. That's a good idea. I can prove that. I wouldn't think that's feasible. You can imagine like you have two classes, right? The majority error cannot be bigger than 50%. That's why. Why? Because if your class is not balanced, there must be someone over 50% and the other one less than 50%. If you use majority to do the prediction, then the error must be less than 50%.
But if you have more than two classes?
If you have more than more than k classes, if it is balanced, then the majority error is like 1 minus 1 over k, right? But if it is unbalanced, what will happen? At least someone is bigger than 1 over k. Right? So it must be less than 1 minus 1 over k. Okay. So this is kind of a simple mathematics. You can try that. It's an interesting investigation if you're interested in that. But anyway, in any case, it provides another way to define the purity, right? And also, let me introduce another measurement for purity. This is called a Gini index. So Gini index is another very widely used metric for purity, and it is by default used by the CART algorithm. We mentioned that before. It's called classification regression tree. The CART algorithm is very popular, maybe even more popular than ID3 algorithm. So let us look at the definition of Gini index. So for binary case, the Gini index is defined as 1 minus p minus squared plus p plus squared. So here p minus and p plus are the negative example proportions and the positive example proportion as well. Yeah. And if we generalize the definition to like k classes, then the Gini index is defined as 1 minus the summation of the square of each label proportions. So p1 squared plus p2 squares until pk squares. Oh, sorry, this should be pt squared. Bear with me the typo here. So now let us look at whether Gini index can reflect the purity as well. So first, the Gini index is always less than 1. Can anyone see this? So first, p plus p minus plus p plus is 1, right? And p minus and p plus are both less than 1. But now, if you take square over each of them, so their scale is reduced. Then when they're added together, they won't be bigger than 1. It can only be less than 1. So Gini index is always less than 1. So and it's bigger than 0, right? So let us consider the most pure case. So suppose we have all the examples labeled as positive. Then what is p plus? 1, right? And p minus is 0. Then what is Gini index? 0, right? And similarly, if all the examples are negative, p minus is 1, p plus is 0, Gini index is 0 as well, right? So now I can say, because Gini index is always bigger than or equal to 0, when Gini index is 0, which is its minimum, the purity is the largest, right? Because all the examples have the unique label. And on the contrary, if half of the examples are positive and the other half are negative, what is Gini index? Half, right? Because p plus 1 over 2 squared 1 over 4, p minus 1 over 2 squared 1 over 4. Then the two terms adds up to 1 over 2. Right? Subtract 1, it gets 1 over 2, right? So it's not hard to prove that when you have equal label proportion, Gini index reaches the maximum. But as we can see, the Gini index will have the equal label proportions. We reach the worst purity, right? Smallest purity, because half of the examples are positive, half of the examples are negative. So now we can.
What is an ideal value of the Gini index?
What do you mean by ideal value?
Like, what is preferred here?
Of course, to be 1, right? Because we want our data to be as pure as possible. If it is purely labeled, there is only one label, right? So either p plus is 1 or p minus is 1, then Gini index is 0. Right? But on the contrary, if the purity is very bad, right? All the labels take the same portion, then the Gini index is the largest. So now we can see the correspondence between the Gini index and the purity, right? The larger the Gini index, the worse the purity. Or in other words, the smaller the Gini index, consider the extreme case that p plus is 1, then the Gini index is smallest and 0, and purity is the largest, is the best. So now we actually find another way to measure the purity as well, right? Gini index. So now question, how can we define our new game based on Gini index? An idea? Yeah, exactly the same thing, right? To give you a concrete example, like if I have 15 positive examples, 5 negative examples, what is Gini index? You just compute the negative proportion, which is 5 over 20 t squared, minus positive proportion, which is 15 over 20 squared. This is Gini index, right? And then, based on Gini index, we can define our gain. Simply replacing the entropy by Gini index. All the other things are exactly the same. So now we have another variant of decision tree.
So based off of that previous example, could you go over what's SV and what's X in
here?
Yeah.
So actually, we can take 1 or 2, right? Or 0 or 1. So positive meaning v taking like positive, v taking 1, and minus meaning v being like say 0, right? So SV will have but here we haven't performed the split, right? We only have the total set S, which contains 15 positive examples and 5 negative examples. But if like you perform some split using some attribute A, such that you give for some specific value, you have like 6 examples. For the other specific value, you have like 14 examples. And for the 6 examples, say it can further contains like 2 positive and 4 negative, then you can compute the Gini index for each subset as well, right? And then you just use this equation to compute the reduction of Gini index. It's very similar to entropy, right? The larger the Gini index, the smaller the purity. The smaller the Gini index, the larger the purity, or better purity. So the reduction of the Gini index indicates the improvement of the purity. Any other question at this point? Okay, good. So now I can say, actually based on different measures of purity, you can implement different variants of decision tree immediately, right? You can simply implement a algorithmic framework, i.e. 3, that just replace one line of code. That is how to compute the gain for features, right? But every time when you select one gain, you just calculate the gain for all the features and pick up one with the largest gain. Select that as the best feature to split the data. That's the idea. Does it make sense? Okay. Everyone is comfortable. So the second topic is to handle the missing feature values. This is actually pretty common. And in your future practice in machine learning, you will always see such kind of situations. There are some examples don't have feature values, either in training or in test procedure or in both cases. And what should we do? Right? Say in our previous example, we want to learn a decision tree to predict whether I'm gonna play tennis according to the weather conditions. Right? What if in the data record for the 8th day, we don't know, we missed the record for the outlook feature. I don't know whether that day is sunny or raining or just cloudy. I don't know. And how should we deal with such kind of missing example, incomplete example? So let us first talk about the training piece. So what if in the training procedure, I have some example with missing features? What kind of strategy do you have in your mind immediately? Well, okay, this is a most straightforward way and pretty effective, I admit. But you will lose training examples. I don't want to lose training examples. For instance, it take me time, take me energy, even spend me money to collect such a training example. I don't want to discard them directly, although it has some flaws, it has some problems. Then how do we deal with that? Excuse me? Yeah, that's one answer, right? So the basic strategy, from a strategic point of view, we're trying to complete the missing feature value, right? So how to do that? One idea, just as you said, using the most common value of the attribute in the whole training data set. We just collect all the examples without missing that particular feature. And we just count which value is the most common, we just fill it. And a more refined version is to look at all the examples with the same output. Like say, for this incomplete example, we know its label is no, right? I finally determined not to play tennis that day. Then I just look at all the negative examples. And among those negative examples, I pick up the most common feature value and fill it. That's the two commonly used approach. And but here I want to introduce you a more elegant approach using the fraction counts. So these two methods, although we utilize the information from the remaining examples, right? But every time I just consider one possible case of the feature value, right? We do not consider all possible feature value cases. To address this problem, we can use the fraction counts of attribute values. What is fraction count? We just look at all the examples without this particular feature outlook missing. Then it turns out, okay, we have 14 examples, and from 40 examples, 5 examples, their outlook feature is sunny, 4 overcast, and 5 rain. Then we just create a fraction count for each particular feature value that can be taken, 5 over 14, 4 over 14, and 5 over 14. And then we duplicate this missing or incomplete example by 3 fractional examples. So say, for each of these new examples, we fill the missing feature with a distinct feature value, right? Sunny, overcast, and rain. But obviously, we won't count this complete example as a whole example because it has a chance, right? In total, it must take 1 example together, right? So we assign a fraction count for each of these new examples. So now we replace the incomplete example by 3 fractional examples. And then we just put throw the 3 fractional examples in our data set for training. That's it. And in this case, you say because all the 3 fractional examples consist of all possible distinct feature values, right? So we imagine that we take into all possible cases into account. So it tends to be more robust.
Wouldn't it like mess with the validity of the tree because the other attributes would get more data supporting them? Like that it was.
You mean this one or this one?
Like all this on the right, like mile high.
No, that doesn't matter. Because if you for this particular feature value, right? For this particular feature value, high, 3 high, right?
Yeah.
You can add the fraction counts together and it still ends up with 1. So the consistent with 1 incomplete example. Right?
Okay.
So remember, when we duplicate 1 incomplete example into 3 fractional examples, all the remaining features are the same. Right? Remaining feature values are the same. 3 mild, 3 high, 3 weak, 3 labels.
But they're all fractional too.
Yeah, the fraction too as well.
If the output was uncertain, would we still do this, or would we just throw it out? So instead of a no, it was just a question mark.
Yeah, no is fraction mark. So the calculation won't be affected, but the calculation you need to be aware is we'll count, say, positive examples, right? And you need to add the fractional positive example as well. So for all the other like, complete examples, if there is 1 complete example, you just add 1, right? But if there is some fractional example, say 5 over 14, you need to add 5 over 14 rather than 1. That's the difference.
Yeah, I understand the fractional part. I'm just wondering, in this case, we have the outlook. We don't know what it was. The training data is incomplete.
Yes.
If we had training data where we didn't have the label, we didn't have the positive or negative.
Oh, that's problematic. Yeah, that's a problematic. That's a easy. That's definitely easy. That's not solved by this strategy. But you can work out some.
Throw it out.
What?
We would just throw it out.
In some cases, you can just throw out because you don't know the label. If you give the wrong label, then this example actually has a bad effect into the training. So I would rather throw it out. And another strategy is called semi-supervised learning. You mentioned that. Semi-supervised learning essentially tell you that I do not give you the label information. And can you incorporate this unlabeled example into the training procedure? But that's another type of story. So when the label is missing, well, I won't suggest you to use this kind of strategy because label is a very important guidance for you to train a accurate predictor. Although, of course, technically speaking, you can use the same kind of way to complete the label. And
So instead of using fractional counts, we use them in the information game to choose the label that's needed for the least amount of information gain.
well, that's an interesting idea. You can definitely do that. But I can tell here, just to give you several common use approaches. You can definitely do use information gain to complete the feature values. That's cool. That's cool, actually. So there's this is also a research area. Although it's not that active, it's not that active. People research how about to complete missing features, and some other strategies, including using k-means algorithm to cluster example first into different clusters and then assign the missing feature with the feature inside the same cluster. There are many ways, but using the three mentioned here are the most common choices, and in like 90% case or 95% case, it is okay. It is enough. Yeah. Any other idea or questions? Okay. Yeah. If you're still feel uncomfortable fractional counts, just do an exercise. Right? Suppose, like you can use our previous examples, training a decision tree to predict whether to play tennis, and suppose you like wipe out some feature value and use a fraction count, and you can calculate positive proportion, negative proportion, and calculate the information gain. It is followed exactly the same way. Leave it as an exercise for you. And next question is that, what if at the test time, if a test example has a missing feature value, what should we do? Any idea?
You're using the most common value of fraction. I mean, based on the training, otherwise,
yeah. If you use the first two approaches, two strategies, the same thing, right? You just complete the missing entry, missing feature with the most common values. Then you do the prediction. That's it. Right? So now, if we use fraction counts, what should we do? An idea?
So you kind of go down all three branches, see where you end up, and then I guess you have sort of like weighted.
Yeah, exactly right. So you just use the same method, but for fraction counts, you end up with like three fractional examples, right? For each fractional example, you got a prediction, and then you have weights according to the fraction counts. You do the majority vote. That's it. Right? So, for example, if I want to predict this example rather than use it for training, right? So if I suppose for this fraction example, my prediction is positive, and the remaining two are predicted as negative. Then for positive example, because its fraction count is 5 over 14, so its weight is 5 over 14, right? And for the other two, suppose they're predicted to be negative, and then the total weight is 4 over 14 plus 5 over 14, which is 9 over 14, right? Then we choose the one with the biggest vote. That's it. Similar idea. And then any questions so far? Yeah. If you have multiple labels, then I guess you have multiple types of predictions, right? And each particular predictions are grouped according to their fraction counts, right? And they just compare which weight is larger. You choose the label with the largest weight. Any questions so far? Everyone is good, right? Okay. So the third topic. So the third topic is to deal with non-Boolean features. Well, we discussed it a little bit in the previous lecture. So now let's first consider categorical features. So in our previous case, we have categorical features like all it can take three distinct values, Sunny, overcast, and rain. So during the tree construction, we create three branches for this feature. Then the problem is that, what if the categorical feature has many distinct values? Right? Suppose we have like 1,000 olives, 1,000 types of olives. Then during the tree construction, we have to create 1,000 branches. And in many other applications like advertising, right? Many categorical features, like different advertiser and different brand. Like you have 10,000 brands. That's not surprising. Then you have 10,000 branches for a tree. That makes your tree too large. It breaks that destroys our principle, Occam's razor principle, to make our tree to be as small as possible. Now how can we deal with that? How can we deal with that?
Cut out the least most commonly found attributes.
Well, that's definitely one solution, right? But we can consider, like, how about if we don't want to drop any information in features? How can we do that?
Combine like super labels where you have sunny and overcast for one branch or some other combination.
Yeah, very close to the commonly used strategy. Very common. So we can actually convert for each specific value of the categorical feature into a binary feature. That's what you're saying. So we can convert outlook into a binary feature that whether outlook is sunny or not. That is either 1 or 0, right? And similarly, we can get another new feature, which is whether outlook is overcast or not. The second type of Boolean feature, right? And third type of Boolean feature is whether outlook is rain or not. So you say we have 3 distinct values for a categorical feature. We can turn it into 3 new Boolean features. And whenever you use those Boolean features, you can at most have 2 branches. You won't expand the tree to be too wide. So in general, if you have like a k, like a categorical features with k distinct values, you can turn it into like k Boolean features. And then now you replace the original categorical feature by this k new Boolean features through the training data set. And you create a decision tree.
So you potentially increase the depth a lot though. You have 1,000 features instead of 4.
Yeah, very good. Very good insight. Yeah, you're right. And later we'll explain how to stop growing your tree to be too deep. That's an issue. That's definitely an issue. But let us solve the problem one by one, right? So first, this is a common use trait, right? For if a cardinality for a categorical feature is too large, we can turn them into many Boolean features. Then we can ensure that our tree always have 2 branches. And a more efficient method is to first group values in disjoint sets and then create them into Boolean features. See, if I have like 1,000 categorical feature values, I like to partition them into like 1 to 200, and 200 to 400, 400 to 600, right? And then I convert feature to be like if this feature is between 1 to 200, or between 200 and 400, between 400 and 600, and you have even less Boolean features. So this is one common use trick. And for numerical features, as we mentioned before, we can use thresholds, or we can create many beans, right? And to create new Boolean features that whether this particular numerical feature value falls in some specific bin. Any questions so far? It's pretty common to use trick, right? But it's very straightforward. And okay, so the last topic is overfitting, which is very important. And actually, everyone should design their machine learning algorithm to avoid overfitting as much as possible, and you will know why. So to illustrate overfitting, let us assume our target function is a kind of first big function. So first big function is a type of Boolean functions with some features. So a Boolean function means that the feature value is Boolean, either true or false. And also the output of the function is Boolean, either true or false. So this is one example of the first big function with 2 features. So the first fit function simply returns the value of the first feature. All the other features are irrelevant. So we can say, from this example, the function value y is simply equal to the feature value x0. It does not need to consider other feature values. So now if you use ID3 algorithm to create a decision tree, you will end up with this decision tree. You say, okay, it's actually has just one internal node, which is x0, and true or false. And you can run this algorithm in your brainstorm, in your brain, and to confirm the correctness of this tree. So this is a simple case, right? For two features first fit function. Now suppose we extend to the general case, like n feature first fit Bloom function, and suppose we have all 2 to the n examples for training. What will be error for any future test examples? So first, we need to be aware. So we have n features. Then how many examples at most we will have in the whole instance space? How many? Yeah, 2 to the n. You're saying 2 to the n or 2 to the n?
Yeah, no, 2 to the n.
Right. Because every feature can take 2 values, right? So first feature can take 2 values, and the second feature can take 2 values, the third feature can take 2 values. So you multiply all those 2's together by n times, right? So I have 2 to the n possible combinations of the feature values. Each specific combination of feature values corresponds to one input, right? One input example. So in total, in the whole instance space, you have 2 to the n examples in total, right? So that means no matter what kind of examples you have in your instance space, it will be included in this 2 to the n examples. So now if I train our decision tree on this entire instance space, what's the training error? 0, right? Because decision tree can perfect fit data. Remember, what is the stopping condition for decision tree? ID3. When all the examples have the exactly same label, right? That means no matter what kind of training example you use for test, use your decision tree, it will always reach at a leaf node with pure label. That means you have a correct prediction. Otherwise, the tree won't stop. Right? Everyone is good at this point, right? So now that, because I have used all the examples, all possible examples in the instance space to train the decision tree, and if I use any example from the instance space to make a prediction, the prediction error is 0. Then if I choose any test example belongs to this 2 to the n example as well. So the test error will be 0, right? Because the training set consists of all possible examples in instance space.
This is for the binary example, right? I mean, we can make decision trees that don't exactly even with all of the examples.
Yeah, this is for binary example. Because we're talking about Bloom functions, right? This is just some ideal case for illustration. If we can use all possible, again, let me repeat, right? If we can use all possible examples in the instance space to train, because decision tree can 100% fit the training data, so the test error will be 0, because test example will be included in the training set as well. So now we can say, if the data is perfect and you have enough data, 100% of fit data is not bad, because the test accuracy, the test will be consistent with the training accuracy. But now, things change when we have a noise data. And noise data is actually we need in practice. So now let us assume very simple noisy case. Right? Suppose we still have these 2 to the n examples in the entire instance space. Okay? But now, the training and test examples both have their labels randomly corrupted. See, in the training set, these 2 labels are original f and t, and now due to the random noise corruption, they are flipped. And similarly, for the test examples, the output for test examples are randomly corrupted as well. And the random noises are assumed to be independent. That means even for the exact same input, due to the random noise corruption, the training label and test label could be different. Now, obviously, your prediction could be different as well. Now, let us observe in this kind of case, what will be the test error? Here's the result. So, we assume the output corrupted in both training and test examples are with probability 0.25 or 1 over 4. And then we examine when we vary different number of features in our first big Bloom functions and how the test accuracy change. So these are standard error bars. So you can imagine when we increase the number of features, the entire instance space are larger and larger. Okay? 2 features, the entire feature space, the entire input space is 2 to the 2, right? 4. 3 features is 2 to the 3. And the 4 features 2 to the 4. So actually the instance space grows exponentially larger and larger. Right? So you can imagine, okay, the prediction will be